Okay, so I've got all of the labs and kind of general things up here to start off with. So you've got the safety and then no glassware. You might have some general lab questions, which we'll talk about in a second, in that safety category, like intermolecular forces, that kind of fun stuff. And then there are all the labs. Okay. So general information and safety. I do expect you to know our general bond types, so our covalent, polar covalent, and ionic, and how to identify them quickly from an individual structure. Okay, so you should be able to do that, hopefully at this point, really fast. And then also intermolecular forces, same kind of deal. Okay, so you should be able to identify all of those fairly quickly. Do you guys need me to review that? So we'll say no. And then safety information, lab coat, goggles, long pants, shoes, kind of the standard stuff as far as that goes. I guess, do you have questions about safety things? Okay, more than likely safety and intermolecular force type question, or directly questions, will be probably multiple choice along those kind of guidelines. With the melting point lab, the primary thing that you'd be looking at there is pure versus impure. So if you obtained a pure or a melting point, what things would symbolize it being a pure melting point? What would you look for? Okay, you had a narrow range. Narrow would be the key word that we'd probably look for, but small works just as well. Narrow range, what else would you look for? I don't like higher. Fix that. Closer to the literature value. Okay, which does mean it would be higher than the impure. But if you don't have an impure to compare against, okay, saying higher isn't going to get you credit. Okay, if anything, if you write higher for describing the pure melting point, I will take off points. Okay, it needs to be accurate. It's not just higher and lower. Okay, it's always a comparison. If it is impure, what would we be looking for? Okay, again, our key, our broad range. Hope none of that's being recorded. We're getting a broad range because we're disrupting the intermolecular forces, so we see a larger range associated with it, and we see a lower value, but lower than the literature value. Okay, so again, it's a comparison. Okay. You should be able to explain why those observations are changing. So you're looking at how the intermolecular forces change. Okay. The next part would be looking at experimental observations. So what we just discussed, that's kind of identifying what you would see. The big question that you'll probably see, and there's a bunch of them like this on the practice exams, is looking at identifying a compound. So that lab was about obtaining melting points, in general observing what pure and impure was, and then being able to identify the compound by doing a 50-50 mixture. So if you take a pure unknown and you mix it with a pure known, okay, if your melting point comes out exactly the same, no change, that means whatever the known was and your unknown are the same. Okay, because you mix some of the exact same substance with another substance. The melting point's not going to change. Okay, if the range changes, or if the melting point changes at all, that means those two compounds were different. Because what you ended up doing was making an impure mixture. So of course the melting point changes. Does that make sense? So when you get those kind of questions, make sure you read them carefully to match up what melting point ties to what. That seems to be the most confusing part about it, is students kind of guess, or not quite guess, but say, oh, I already answered this question in the group activity or in the pre-lab or in-lab. Okay? Just because the format of the question is the same does not mean the question is the same. Read the question carefully, make sure you answer what's being asked, not what you think I'm asking. Okay? Questions about melting point? Okay. Crystallization almost always throws people for a loop because everybody thinks I'm asking what's the ideal curve. Okay, so the biggest part of the crystallization lab is going to be looking at that solubility curve and trying to identify important things off of it. Okay, so when we go through and try and recrystallize something, what we're really relying on is variable solubility. Okay, where our compound is highly soluble at one point, and at another point it's lowly soluble. How about just not soluble? I guess that was a good suggestion. I wanted to stick with the soluble term, so, but yeah, not soluble or insoluble. So we need to change that somehow. When it came to recrystallization, we did this pseudo-passively. So we did that by changing the temperature. So it's highly soluble at high temperatures, and it's not soluble at low temperatures. So low solubility, low temp, high solubility. Okay? So if we went back to our curve, what we need to do is find something that matches that. So we could take either of those two options. We could start with high solubility, high temp. So where's the easiest thing for you guys to find on this curve? High solubility or high temp? It's up to you. Either one's the same. Okay, high solubility. So where is high solubility going to be on this curve? Okay, it's going to be up at the highest part of this. So we're looking at something that's very soluble up here. So we walked through this in recitation, trying to specify all the obvious things on the graph, because it'll minimize your mistakes. What happens if we're down here, at the bottom of that curve? Now we're insoluble, or I'm not sure I can fit insoluble there. We'd be insoluble or not soluble. Okay, at the bottom. We could then go through and say, at that point, we are cold or low temp. Over here, we're looking at hot or high temp. So if we go to try and match things up, at high solubility and high temperature, what curves match that? A and C. So we're looking at somewhere up in that quadrant. Both those curves match. For it to be an ideal recrystallization solvent, we also need it to be not soluble at low temperatures. So we need to be something that matches in this quadrant. What's the only curve that matches both those sections? C. Okay, so our ideal recrystallization solvent is C. Okay, so the other phrasing you would see there is ideal crystallization, or something along those lines. Okay, what if I changed the question though? What if I asked, instead of the ideal crystallization, I asked for the ideal insoluble impurity? The ideal insoluble impurity is going to have what characteristics? Insoluble, that makes sense, at all temperatures. So we could go back up, and we're looking at insoluble, which would mean, since we very nicely wrote that on there, we need to have something that matches down below. What's the only thing that matches? B. Okay. What if I'd asked for the ideal soluble impurity? So the ideal soluble impurity would be soluble at all temperatures. We're looking at the top. What's the only thing that matches that? A. Okay? So make sure you know what the question's asking, which part of the graph we're asking you to deal with. Okay? There's 2 sections, there's a lot of tables, all sorts of other things like that, so there will be multiple versions of the quiz. This is a very easy question to change those options around, okay, to prevent copying on. So make sure you know what your question asks. Okay? Ideally, you shouldn't be figuring out what the person next to you's question is asking anyway, but just be aware of that. Okay? Other things that can show up with recrystallization. So instead of looking at the solvent, we can look at some other things popping up into this. So we could look at solubility of simple cases. Sand, salt, and water. Okay? Pretty much everybody's had experience with sand, salt, and water. which means I would expect you to know the solubility of each of those compounds in each other. Okay? So you had a lot of questions, I think, in the group activity, and actually I think they're all in the group activity, looking at how to separate varying mixtures of sand, salt, and water. Okay? So what can you tell me about the solubility of sand? It's insoluble in water. Salt? Soluble in water. Okay? So if we're going to try and separate those, you need to be aware of those possible options. Okay? Questions about those possible combinations? Okay. Last thing that you could see would be lab issues or timing or conditions when dealing with the recrystallization. Okay? So this is going back over the procedures and making sure you understand why you were doing certain things. Okay? So when you first start the recrystallization process, what did you do? What was the very first step in your recrystallization? Nobody? Okay, I can give you the easiest first step. You probably obtained some crystals. Then what'd you do? Okay, you could set up a filtration system, but to filter something, what do you need? You need a liquid and a solid to be able to filter something away from. At this point, all we've got are crystals. So what did you need to do? We need to mix it with a solvent. What's the goal of mixing it with the solvent? To dissolve it. We're looking at our solubility differences. So we'd want to dissolve our crystals in the solvent. However, if we try to dissolve our crystals at low temperature, what's going to be the problem? We're going to have to add a lot of solvent. If we add a lot of solvent, our compound sure will dissolve, but we need variable solubility. We need our crystals to come back out of solution. If we add a lot of solvent, what we're trying to look at is that temperature change. So we can take a lot of room temperature solvent and cool it down. The difference in temperature there is so small that more than likely you wouldn't get any crystals back. So when you go to dissolve your compound, your first step is not to just dissolve it, but to dissolve it in as hot a temperature as possible. So it's a hot dissolving process. Okay? If you had an insoluble impurity, is it ever going to dissolve? No. So how do you get rid of the insoluble impurity? You're going to have to filter it. Okay? But does filtering get rid of it? Just a filtration. What if it was cold filtration? You have to specify the temperature. If you drop to cold temperatures, you'd be down in this situation with our insoluble impurity. Okay? Which means your insoluble impurity and your crystals get filtered out. You didn't purify it. Okay? So what we have to do is filter when those two substances are as different as possible. The place where they're different as possible is where the temperature is hot. So to remove an insoluble impurity, we have to do a filtration, but a hot filtration, so that we don't lose our compound. Okay? How would you remove a soluble impurity? We need to do again a filtration, but we're again looking for a difference in our solubilities. That difference is when it's cold. So we would do a cold filtration. Okay? Does that make sense? That extra piece of information is critical to showing that you understand that technique. Okay? Yes?
So you're going to say, like, given these impurities, what type of filtration will you use?
Yes.
Okay.
Yes. So, and I'll repeat that for those of you that couldn't hear this if you're watching on YouTube. I will provide you a certain situation. I'll say you have your unknown compound with an insoluble impurity. How would you remove that insoluble impurity? Okay? That's going to require a hot filtration. Okay? So that was something to do with timing and conditions. So when do you do that filtration, which is ultimately dealing with temperature, which is your condition. The next issue would be lab issues. What if your compound, your impurity, happened to pretty much match the solubility of your compound, of your target compound? Okay. At that point, we're in a very tricky situation because we don't have an easy circumstance in which to separate those two based on their bulk solubility differences. Okay, because at hot temperatures, they're pretty much the same. At cold temperatures, they're pretty much the same. The only way we can separate an impurity that has similar solubilities is if we have a very small amount of it. So a recrystallization is typically used as a very refined technique. You're removing small amounts of impurity. If you have a lot of impurity there, you can't get rid of it unless it's one of those extreme ideal circumstances. So ideal soluble or ideal insoluble. Okay? Does that make sense? So when does a recrystallization fail? You have a lot of impurity and it has a similar solubility to your target compound. It has to be both of those. Do you have a question still? So cold filtration, so we can go back to our curve. The goal of filtration is to ultimately separate our two compounds. Okay? So if I'm going to move to cold temperatures, what compounds could I separate? So first off, C would represent our ideal situation, so that's probably our crystals. Would I be able to separate compound B at cold temperatures? Why not? Similar solubility. So what I would have to be able to remove, or the only thing I could remove, would be compound A. What can you tell me about the solubility of compound A? Highly soluble. Okay? So a cold filtration would help us remove high solubility compounds or impurities. Okay? Make sense? All of it comes back to this graph, which is why I'm 100% guaranteed this graph will show up in some form or another when it comes to recrystallization. Okay? So pretty much any question I ask, you can find that answer by applying the information given in the question back to this graph. Okay? So take advantage of using that graph, being able to interpret it, or just memorize the crap out of it. Okay? That's fine too. Okay? Other questions about the crystallization technique? Okay. Then we get infrared spectroscopy. As difficult as spectroscopy or IR spectroscopy ends up usually coming across, it should be the easiest part of the exam because you're given a table of IR spectra or where certain bonds show up, and you're given a spectra. You just have to match. It's a matching game. Don't make it any more difficult than that. Okay? So, two ways that we can ask the question. I can give you two compounds and say, identify the characteristic signals that would allow you to differentiate these two compounds. Okay? Well, IR gives you information about what? Bonds. So what you need to go through and do is for each compound, given the structure, you can then identify all the bonds because the structure is drawn right in front of you. So identify all of the bonds all the way through it, and then compare your two columns of what are they? Bonds. Okay. If the bonds are the same, that's not going to be particularly useful to tell the difference between them. So you could cross those out. If they're different, now you can go and look up the table. Is that difference something that we tell you in the IR table? If it's not in the IR table, will you be able to use it to identify them? If it's not in the table? No, because you don't have that information, so don't worry about it. If it is in the table, identify where it shows up, and you're done. Okay? The other way that you can end up seeing this is kind of a multiple choice question. Given an IR spectrum, I can give you a multiple choice option of 4 or 5 structures. You would then go through and analyze the IR spectrum with the IR table, okay, and match up the different frequencies to what bonds those would correspond to. Once you've got the general bond types shown in the IR, go and look at all the structures, and again, it's just matching. Match to the one that matches the best or all of the IR peaks. Okay? If it doesn't match, that's not your answer. Cross it out. Okay? Make sense? Okay. Extraction. This is another one that typically causes students a lot of problems. It's ultimately a solubility question, and it's looking at intermolecular forces. So when we dealt with recrystallization, it was a passive solubility, meaning we just changed our solubility with temperature. When we move into extraction, we're going to do an actual chemical reaction to change the structure. If the structure changes, what happens to the intermolecular forces? Good answer. They also change. If those change, that's also going to change the solubility. Okay? So the idea is to match up those changes and see how solubility changes as you move through it. Okay? So you can expect potentially a flow chart showing up, okay, saying put in structures, draw structures in each individual position, like we did in lab. Pretty sure that was in your group activity. Maybe it was definitely in your in-lab. For sure you had it there as well. Okay, so go through, review those flow charts, and understand why things are changing. Okay, you can expect to possibly be responsible for an acid-base mechanism. Okay, so given one compound reacting with an acid, what's the mechanism? How do you show the electrons moving to change to give you to your products? Okay. As far as what types of things that you're really responsible for in that case is looking at the two primary functional groups that we were concerned about. You looked at carboxylic acids. We also looked at amines. A carboxylic acid is a carbonyl bound to an alcohol. That whole functional group is referred to as a carboxylic acid. How does that end up acting? How is that chemically reactive? Are there any partial charges in this structure? Yeah, where are those partial charges? Okay, the carbon is partially charged. What partial charge does it have? Partially positive. Why is it partially positive? Because the oxygens are electronegative. Keep going. If the carbon's partially positive, what do you think the oxygens are? The oxygens are probably partially negative. Okay. What does that mean for the hydrogen? It's also losing a lot of electrons. Okay. So we get ultimately 4 sites of reactivity. If we were going to try and predict the reactivity for each of these, would we expect oxygen to share its electrons with anything? Is oxygen particularly willing to share electrons? No. Not really. So if we're going to look at reactivity, let's put the oxygens on the back burner and shift to the carbon versus the hydrogen. Which of those two atoms is likely going to be more reactive? The atom buried in the structure or the atom on the outside? The atom on the outside, we're probably looking at the hydrogen being the most reactive. So that hydrogen is partially positive. So that's very, very similar to, say, maybe H+. Where do we get H+ from? So as a sample reaction, we could get H+ from this species. What is this species? What's that? I heard it. It's an acid. So what do we think the carboxylic acid acts as in most reactions? As an acid. Okay. What do acids react with? Bases. What's a good base that we could potentially react with our carboxylic acid? OH-. Okay. You might also see it written as NaOH. Okay. Why do we typically ignore Na or sodium ion? It's typically a spectator ion. How do we know it's a spectator ion? You go all the way back to your solubility rules. Rule 1, all group 1 metals, for example sodium, are soluble, meaning they don't do anything in most reactions, or the ions don't do anything. Okay? So if we do a reaction here, we've got that negative oxygen and that partially positive hydrogen. What would we do to show the mechanism? Show the flow of electrons from our source of electrons to where it lacks. We're now sharing electrons between oxygen and hydrogen. How many bonds can hydrogen have? Only one. How many bonds does it have currently? 2. So we have to break a bond. What bond do we break? Where should those electrons go? Towards the oxygen. Why should they go towards the oxygen? Oxygen's more electronegative than hydrogen, and the second reason, hydrogen had too many electrons around it to begin with. We need to get those electrons as far away from it as possible. What does that do to our structure? That oxygen just gained electrons, so it's now negative. We end up with water. What can you tell me about this compound? Nothing? Name that symbol for me. Negative. What things are negative when we're moving into chemistry? We can give them a fancy name. Could go that far. I'm going simple. What's that? Could look at them as electrons, but those electrons are on an atom. It's an anion, or a negatively charged atom, an anion. And what? Ion. What kind of force would an ion have? Ionic forces. Ionic compounds are also typically called salts. If it's a salt, what does that mean about its solubility? It's soluble in water. Whereas our compound to start off with was an organic compound, not typically soluble in water. We've now changed our intermolecular forces. Our compound has gone from being organic soluble into water soluble. Okay, because we've changed that structure. Does that make sense? Okay. So that would be the carboxylic acids. We'll go a lot quicker through the amines. Your amine functional group. Put an R for whatever organic compound we're looking at. More than likely you'll see it as a primary amine, so NH2. Amines act as bases. If it's a base, they react with acids. What's a good acid? We could add HCl. What part of HCl makes you scared? The H. H what? H plus. Why is the hydrogen positive? Why is chlorine taking the electrons? Chlorine's more electronegative than hydrogen. Noticing patterns. We've been trying to build on these same things again and again and again. Okay? So what we can do is have nitrogen share its electrons with that hydrogen to help stabilize that positive charge. Hydrogen now has too many bonds, so we can push those electrons all the way onto the chlorine officially. My spacing. Nitrogen started neutral, shared its electrons with something else, which means it's now positive. So if we look at what that means, it lost, so that would be a negative. Electrons, what charge are electrons? Negative. Negative times a negative equals positive. Okay? And then we could also draw, if we really wanted, the chloride out there. Okay? What can you tell me about this species now? What is that called? It's a cat what? Ion. Okay? If it's an ion, what intermolecular forces does it have? Ionic. What else do we call ionic compounds? Salts. What do we know about salts? They're soluble in water. Okay? I know it's repetitive, but that's what all of this stuff is. Okay? It's going back to those basic intermolecular forces and trying to apply how that shifts out into what we observe. Okay? Does that make sense? Questions about extraction? Okay. The other big lab that was kind of a problem or more difficult with, typically more difficult for students, is the alkyl halides, or looking at substitutions. You are responsible for mechanisms, which I didn't actually draw up on here. Sorry about that. So let's add that as a line. Okay, you are. Is that how you spell mechanism? That's weird. So you are technically responsible for mechanisms. The other big thing that you'll see, if you don't see an actual mechanism for these reactions, would be looking at trying to decide what type of mechanism it went by. So what we could do is look for stable carbocations. Okay? So if you can form a stable carbocation, it's an SN1 mechanism. Okay? If we look at steric hindrance being an issue, we'd be looking at an SN2 mechanism. Okay? What things would form stable carbocations? Tertiary substrates or secondary substrates. Tertiary being much more stable than secondary. What things have the least amount of steric hindrance? Okay, we've got zeroary, primary, secondary. Does that all fit on there? Yeah. We could potentially see tertiary, but that's so rare when it comes to steric hindrance that in most cases we ignore that. Okay? The next big part of this was looking at leaving group abilities. Okay, so in this lab we tested a bunch of bromo and chloroalkanes, and one of the comparisons that you were asked to make was the relative rate of a bromo compound versus a chloro compound. And what you should have seen was the bromo compound reacted faster than the chloro compound. Okay? Why? So there's a couple answers that you could put in here. I know in previous semesters I was really picky with it.
Now, you're saying the bromo is faster than the chloro?
Yep.
Because could be that what is the chlorine is a lot smaller, but it's more like a negative.
So the argument that you're going to make is a stability one. Bromide is a better leaving group than chloride because if you look at the negative charge in your product, the bromide disperses that negative charge over a much larger area because bromide is bigger than chloride. Okay? Size almost always trumps electronegativity. The bigger that group is, the more it can stabilize that charge, which is why resonance is a really good stabilizing factor. We're taking that negative charge or a positive charge and we're pushing it across a very large area or spreading it across a large area. Okay? In this case with bromide and chloride, there's no resonance, but it's a size argument. Bromide is much larger than chloride. Okay? That is technically not the correct answer for why it works faster, but that's going to be good enough for us. Okay? You guys don't need to get into the details of that. Okay? If you care, you can ask me later. Okay? So you guys probably won't ask me, but maybe somebody will. Okay? The last big thing that you should have seen with these reactions is that sp2 alkyl halides did not react in either mechanism. Okay? So if we drew out some possible structures here to compare, we can make this fun. Do it all in the same structure. And because I can, let's go ahead and color code it. What can you tell me about the orange bromide? How would you classify that one? We go back and look at the carbon to which it's attached. How many carbons are attached to that carbon? 1. So that halide is a primary halide. Which mechanism would we expect that bromide to react fastest in? The SN2. It's sterically the least hindered. How about the blue bromide? So we can go back to the carbon to which it's attached. How many carbons are attached to that carbon? 3. 1, 2, 3, which means it's a tertiary bromide. Which reaction would we expect that one to not react in? The SN2. Which one should it react in? SN1. Okay? So watch out for those knots as well. They can always throw a wrinkle in answering questions. If we look at the the red bromide, which one is that? That's attached to 2 carbons. We're looking at secondary. Which mechanism is our secondary bromide going to react in? An obnoxious question because it reacts in both. Okay? And if we move to our green bromide, take a look at that carbon. How do we rank that one? It's sp2. Okay. Our primary, secondary, tertiary classifications really only work on sp3 carbons. As soon as we move up to a carbon that has a double bond attached to it, we can call it sp2. The other names you might hear from lecture would be something called vanillic. Okay. We've only stuck with sp2, so we'll keep it that way. Okay. There's another name that you might see floating around out there, particularly for structure or blue bromide. That blue bromide is more special than just a straight up tertiary. What's extra special about it? It's 1 bond away from a double bond, making it allylic. Okay. You're not officially responsible for that in lab, but you could see an allylic question pop up by me telling you this compound is allylic. It reacts fast in an SN1 mechanism. Why does it react fast in an SN1 mechanism? Okay. So, good thought for the one that's blue, but let's change the question. Okay. That bromide, what kind of a bromide is this? It's primary and allylic. This compound reacts fast in an SN1 mechanism. Why? Okay, in an SN1 mechanism, primary cations don't form. This is primary. Why does it still react in an SN1 mechanism? Because it's allylic. Why does being allylic cause it to react fast? Look at the result. If the electrons leave, we're looking at the stability of the carbocation when we're looking at the SN1 mechanism. Whoops. And the answer to most explanation or why questions ends up coming out to be resonance. what we can do is take the electrons from our pi bond, shift them over, and we're now spreading that positive charge across multiple atoms. That makes that positive charge more stable, and because it's a stable positive charge, or a stable carbocation, we can see the SN1 reaction work. Okay? Make sense? Questions about the SN1 reaction? Or, sorry, alkyl halide lab. Okay. So when we move to the alkene synthesis lab, this is ultimately an elimination reaction. You are responsible for the mechanism in this case as well. There were a couple other things that popped up in this. You get stability of the double bond. What makes a double bond more stable? Good call on resonance. That was not where I was going with it, but that's very true. The more substituted the double bond, the more stable the double bond. Okay, what do we mean by that? If we compare this double bond, showing up there, to this one, which of those is more stable, left or right? The right, because it's more substituted. What we're referring to by the substitution with the double bond is anything that's not hydrogen. Those carbons have to have 4 bonds, so they will always have 4 bonds, period. Okay? It's a question of what those bonds are attached to. And in our first case, we're looking at hydrogens. Hydrogens aren't very stabilizing, whereas the carbons are. The argument that we went through in class, which is again technically wrong, but it works, is look at the reactivity of that double bond. If we take the electrons and try and move out, what does it have to move by? What's in the way? A hydrogen atom. What electrons does hydrogen have to block the electrons of that pi bond? Okay, positive is the right idea. It doesn't have any. There's no electrons to block the pi bond coming out. If we go ahead and look at our other case, what atom do we encounter? Carbon. What's the difference between carbon and hydrogen? Carbon's got a lot more electrons. So our double bond comes out and sees electrons. What happens when we get 2 electrons near each other? They repel, the double bond goes back into the structure. Okay? So that structure or that compound ends up being a lot less reactive. Okay? For those of you in lecture, where your lecturer likes to talk about names, what rule are we looking at here? Formation of the most stable double bond. Yeah, Zaitsev's rule. Okay? Which you might see also spelled with an S, but it's usually spelled with a Z. Okay? So given an option during an elimination reaction, you almost always want, or you always want to form the most substituted double bond. Okay, at least as far as lab is concerned. Okay. Other things that we did in the lab was looking at the role of the acid catalyst, which is pretty much grouped with leaving group ability. Okay, because when we ran the lab, we looked at the elimination of an alcohol. To form our double bond. I know this wasn't exactly what we did in lab, but it's close enough. Okay. For that reaction to occur, we definitely have to have the OH break off, but that is a terrible leaving group. So it's not something that happens easily on its own. So we add an acid catalyst to speed our reaction or to facilitate it actually occurring. That acid catalyst activates our alcohol. So we take a lone pair from our alcohol, share with the hydrogen, and we form OH2. What charge would the oxygen now be? It shared its electrons, so it lost electrons. It's now positive. Does oxygen want to be positive? No. What does it do? It's going to steal electrons really well. Okay? And you end up forming water instead of hydroxide. Water is a great leaving group. Why is water a better leaving group than hydroxide? It's a weak base, which is ultimately saying it doesn't melt our face off. Okay? Your leaving group is the same thing as your face. You don't want your face to melt. The leaving group needs to be something stable. Okay? So the acid catalyst facilitates the reaction by activating our alcohol in an acid-base reaction to make a better leaving group. Okay? Should I walk through the mechanism, the whole thing, or do you guys want to refer to your notes? Walk through it? Okay. So with our elimination, I'm going to take a guess at what you guys started with, which I think this is right. We started with 4-methyl-cyclohexanol. We added an acid catalyst. Okay, the lone pairs on our oxygen share with our hydrogen. We form our intermediate. Okay, that oxygen doesn't want to be positive, so it'll steal electrons. It can take them from our carbon. And we end up with a positive charge on that carbon. Okay, we now need to find a way to stabilize that. We don't have resonance, so we're going to have to find electrons somewhere in the structure. This is where we run with the other name for our elimination reactions, okay, which you might see from lecture, is beta elimination. So if we refer to the most reactive part of our carbocation as the carbocation, and we label that as our alpha position, our beta position is going to be either of those carbons. We can't take the electrons away from the carbon because that destroys the structure. Okay? So instead what we're going to do is look for an electron source attached to that carbon. That's where we can look at our hydrogens that are attached. And we can take electrons from our hydrogen to form our final product, which was that 4-methyl-cyclohexene. Okay. What if I had tried to pull electrons from the other hydrogen? Double bond would be on the other side. Is there any difference in those products? No. So I only end up with one product. Okay. What if the alcohol location where it started with shifted to some other position on that ring? You then have to make sure you evaluate and make sure that the beta hydrogens you're removing generate either the same product, or if it's different, how does it change the stability of your double bond? Remember, you always want to form the most stable double bond. Okay? Questions about that? Okay. So I think that's it with the alkene. Can do thin layer chromatography next. Okay, so what we're looking at there's a couple things, or a lot of things that we could look at. You get RF values. How do you calculate an RF value? It's the distance of your spot divided by the distance of your solvent. Okay, that gives you an RF. What's the maximum value you could get? 1. So if you go through and do the calculation, you get a number greater than 1, what happened? You're wrong. Taking it to that next step is a bit far. You're wrong, but all you did was just swapped your two numbers. So flip them around, recalculate, and you'll be fine. Okay? As far as what you might see on an exam, we could draw this out. You'll see your solvent front marked at the top, so solvent. You might see a start written at the bottom, but that kind of is implied. And then you'd see the spot. The distance your spot traveled was from where to where? From the start to the dot. Where's your solvent travel distance? From the start to the solvent. Okay, one of the most common mistakes I've seen is people including this section. Okay, from the bottom of the plate to the starting point. Do not count that. That's not part of your RF value. If you do that, you do get it wrong, and there's nothing you can do to fix that. It's just straight wrong. Okay? If you get a high RF, what does that mean? Did your spot travel a lot or a little? A lot. So if we look at our extremes, if our spot traveled with the solvent, the very top, okay, the distance traveled by our spot divided by the solvent, if the numbers are the same, it's 1. If it doesn't travel at all, 0 divided by 1, 0. Okay? So why did your spot travel far? Because it did not interact with the stationary phase, or the phase that didn't move. It interacted preferentially with the moving phase. Okay? So how would it interact with the stationary phase? You need to know what intermolecular forces the stationary phase is going to give you. What can you tell me about the stationary phase? Just for the heck of it, why not? Wicked polar. Okay? Meaning extremely, or a lot, or very polar. Okay? Which means if your compound is very polar, what's it going to do? It's going to stick to our stationary phase. The polar will interact with the polar, and it stays put. It doesn't move. So if you get a low RF, that means your compound didn't move, which means it stuck to the stationary phase, which means very polar. Okay? What happens if you get a high RF? It didn't interact with the stationary phase, so it interacts preferentially with the mobile phase. Okay? So if it's not on the stationary phase, it's got to be the opposite of polar, which is nonpolar. Okay? The wrinkle that we'll throw in here is this solvent effect. What happens if I make the solvent more polar? All the solvent does is push. If it ends up being a more polar solvent, it pushes more. More polar means more push.
So like it'll go higher?
It'll move higher. What about the order? The order stays the same. A nonpolar compound will always travel the furthest, okay, regardless of the solvent. Okay? So the trick question that will be asked is, here's a TLC plate. Okay, let me, let's just erase that. So if I draw a TLC plate, okay, you might see, let's say, just two compounds, compound A, compound B. Which compound is more nonpolar? A. Okay, so you can see some pseudo double negatives floating in there, so make sure you answer your question right. A is nonpolar. Okay, and B is polar. If I increase the polarity of the solvent, all I'm going to do is push these compounds harder, which means they both move further. The order does not change. A still does not interact with the stationary plate, but it's being pushed harder. So it moves further up the plate. B is getting pushed harder, but it's still polar. It still interacts with the stationary phase more than compound A. Okay? So the order does not change. What happens if I make it a nonpolar solvent? Everything moves less far. What happens to the order? Still stays the same. Okay? So where it gets confusing, more polar solvent, what happens to your RF? It goes up. More polar compound, you have a lower RF. So make sure you're aware of what we're referring to. If we're looking at the compound, more polar stays low. If we're looking at the solvent, more polar goes high. Okay? I know they're opposites. Make sure you keep them squared away. Okay? What are possible stationary phases? I don't think I would ever ask a strict question like this, but just in case. Alumina, silica, okay, those are your common stationary phases. I wouldn't get specific on a mobile phase, but what would you tell me the mobile phase was? It's a solvent. Okay, it's whatever solvent you want to add. Okay, so I wouldn't ask specifically what solvent was used in your experiment. Okay, that's a bit rude. Okay, questions about TLC? Okay. Gas, yeah, there it goes. Gas chromatography, probably my least favorite lab. So as far as the questions that I'll ask, what I would recommend you do, because you won't see any questions in any of the practice quizzes for gas chromatography because it was a brand new lab this semester, is go back through the group activities and the in-labs for possible questions, because those are the types of questions I'll ask about it. The questions will be very similar to what you see for TLC. Why? It's chromatography. Okay, they're both the same principles. You're seeing the same general ideas. Okay, I could ask you to determine retention times. That's kind of straightforward and boring as far as you guys are concerned, because when you guys analyzed it, how did you figure out the retention time? Whoops. So you had your graph. What's the retention time? I know that's sloppy, but deal with it. Retention time is when our compound came out. So retention time for compound, or the first compound here, is 1.5 minutes. What's the retention time for the second one? 4.5 minutes. Okay, so it's just reading it off of the graph. It's not where your compound first starts to go up, it's where you see the peak. Which, if you were in Robin's class, you never saw the peak. But there will be peaks. Okay. If you have questions about that, I can tell you what happened. The order in which things come out. How does gas chromatography separate? Separates based on... It heats it up, so what would cause things to be different based on heat? Close, right idea, but they were liquids. We're looking at boiling points. So gas chromatography separates based on boiling points. The lower the boiling point, the faster it travels through the column, the faster it hits the detector. So if we had to say which of these two compounds had the highest boiling point, which one would it be? Left or right? Our right. This would be our highest boiling point. Okay. Why would a compound have a higher boiling point? Stronger intermolecular forces. It's going to come back. Okay. So almost guaranteed one of the first questions you'll see will be, what are your intermolecular forces? Hopefully you all get that perfect and then realize that you can then refer back to your answer to help you answer all the other questions. Okay? Questions about gas chromatography? Okay. EAS, your electrophilic aromatic substitution, you are responsible for the mechanism. You guys want me to draw the mechanism again? This involves lots of drawing with my finger. I'm good at it. Finger's getting tired. So we'll start with an aromatic ring and an electrophile. The aromatic ring structure could change, the electrophile structure could change. Remember that you're still looking at the electrons in your aromatic ring reacting with the lack of electrons in the electrophile. So when we look at our ring, do any of those double bonds different? No. So, does it matter which one we pick? No. So pick any one you want. Okay? What did you just say? That one. That works. So if we take the electrons out and we say put our electrophile there, what happens to our carbon at the bottom? This carbon. Our blue carbon. It's now lost electrons. It's positive. We need to try and somehow stabilize that. How can we stabilize that? We need to give it electrons. Where do we have electrons? And the pi bonds are going to be the easiest, so we can shift those over. We didn't change any of the sigma structure, so don't start moving anything around, and that will simplify things. You can still draw things correct by shifting everything, but it makes it more difficult and it makes it a lot easier for you to make a mistake. So try to avoid shifting stuff. We didn't touch the other double bond, so we'll leave that there. And our new double bond is here. What happened to this carbon now? It's positively charged. What's the relationship between these two structures? Intermediate's the right idea, but I wanted a key word on that. Resonance. The only thing we moved were electrons. So we're looking at resonance. You should be showing the double-headed arrow in between there. Is our positive charge stable? No, so we'll search for electrons. Where do we have electrons? Pi bond. We now have two pi bonds to choose from. Which one do we want to deal with, top or bottom? Top. Why not the bottom? We just did that. We just go backwards. When you go through and do these kind of mechanisms, I'd highly recommend that you try to minimize, which we already talked about, rotations of the structure, but then also minimize the amount of arrows you're using per step. Try and only move one set of electrons at each individual time. Otherwise, you're going to end up doing all sorts of arrows all over the place. Okay? And you can still do it right, don't get me wrong, it's just, it makes it more difficult. So if you think you can do it right and think it would be funny to torture your TA because they'd have to then interpret everything, have fun. Okay, because they have to grade it, right? Okay. So at this point, to stabilize that positive charge, all we've got are the pi bonds, and those didn't permanently stabilize it. We've now shown all of the resonance, so we have to find a more permanent solution. Okay. One of the things that we didn't do in this case was push the electrons through this carbon, our now green carbon. Why did we not push electrons through that green carbon? It's not quite that it's stable. What's the hybridization of that carbon to start with up here? How many electron groups? It's got 3. What's that third group to? A hydrogen. Did I show any arrows going to or away from that hydrogen? No. So that hydrogen is still here. Ooh, that was an ugly hydrogen. Okay. Why is that particularly relevant? Well, that carbon now in our intermediate is what hybridization? Stick with that. Begins with an S. sp3, because we've now got 4 electron groups around it. Can we push electrons through an sp3 carbon? No. We have to have a p orbital to do resonance. With an sp3 hybridized carbon, we don't have that ability to do resonance through it, so what we end up having is a shutdown in resonance there. So what we'll end up doing is going back and saying, hey, that structure's not aromatic because I can't do resonance through that position. Let's restore aromaticity. We're going to take electrons away from that hydrogen, forming our double bond. And we end up with our final product with our electrophile now on it, and we end up with H+ floating around in solution. Okay? So that's kind of our generic mechanism. When we went through and did it in lab, we added, let's see, where are the... just so that it holds consistent. We started with bromobenzene. Shoot. So if we go all the way back to the beginning, are all of those double bonds now equivalent? Now our positions are slightly different because that bromine is now affecting our overall structure. Okay? So what we're looking at is how this atom affects the electron density in the ring. That atom has more electrons than a hydrogen atom. It can donate electron density in, putting a lot of charge, partial negative charge, at our ortho and para positions. Which means if we're going to do the substitution reaction with a bromine attached to it, our electrophile is going to move to our ortho or para positions, or do the substitution there. Why would it prefer para over ortho? In theory, your lecturer should have talked about this. Not quite, but right idea. Less sterics. There's a steric argument with the electrons from this pi bond trying to come out. Those have to get by the bromine, which has a lot of electron density. So that bromine, the presence of that bromine, prevents the electrons in the ortho positions from reacting very well. So we would see the para reacting better, which is that it's further away. It's just not quite there. Okay? Does that make sense? Okay. When it comes to the mechanism, so we just showed the EAS mechanism. The other mechanism that you're officially responsible for is forming the electrophile, which was our NO2+. That was that acid-base reaction. Should I draw that one out too? Saying some heads, yes. I'm going to erase everything. We started with nitric acid. And sulfuric acid, which is officially H2SO4, but I'm showing it this way to accent the bonds a little bit easier. We can take the electrons from our oxygen, shift those to our hydrogen. Hydrogen needs to lose electrons. What have we formed now out on that oxygen other than that positive charge? OH2, also known as water. What's special about water? It's a really good leaving group. Okay. And the result of that is we get our electrophile. Oof, close enough. I said electrophile. I'll just accept it. We get our electrophile and water. Okay, so that mechanism is a lot shorter. The part of that that's interesting is that we're doing an acid-base reaction at the very beginning. And this species is acting as what in this mechanism? Nitric acid acts as a base. It ends up being a proton acceptor, which makes it a Bronsted-Lowry base, even though it's a strong acid. So that's kind of cool. Okay? Questions about that mechanism? Yes?
Are you going to say, like, draw the mechanism and we'll have to draw it?
So when it comes to mechanisms, can I do it with this one? Yes, I think I can. What you would see, let's see if I can do it carefully.
Like, show the arrows.
So there's a couple ways that I can go through and do it. First way, I will show it with the black arrow. Give me the mechanism to go from your starting material to your product. So that's one way I could ask a mechanism question. The other way I could ask a mechanism question is, say, given, say, this piece, what's the product of that? So complete that arrow pushing. The other way, I know there's all sorts of overlapping things here, is say something along these lines. Provide the curved arrows to go from reactant to product, where I've given you the structures.
So we'll never have to come up with, like, the beginning, I guess. Like, we'll never have to come up with our own, like, mechanism, you know? Like, we'll never have to draw, like, the nitric acid.
I will give you the beginning and the end
Okay.
when asking for a mechanism.
Okay.
And so one of the things that you need to be aware of, and I just erased it, but if you go back to that EAS mechanism that we just did, in that case we went beginning to end, and I should have shown that so you know what kind of question you'd get. It would start off with the benzene and E+, arrow, benzene with E attached. Provide the mechanism.
Okay.
If I added bromine onto it, okay, then we'd start with the bromobenzene plus E+, gives us the bromobenzene with the E attached to whatever position I said. Okay? You, regardless of what you think, where you think the electrophile should go, need to draw the mechanism as I'm asking you to draw it. So if it says the electrophile goes to the meta position, you draw the mechanism where the electrophile goes to the meta position, because that's the product I'm telling you to make. Does that make sense? Okay. So don't answer the questions the way you think they should be answered. Answered based on what I'm telling you to do. Okay. Other questions about EAS. The effects of halogens. So halogens are those in a weird class. They have more electrons than hydrogen. So we would predict them to be what kind of directors? Halogens direct electrophiles to go to which position? Ortho and para, or I'd prefer you to phrase it para-ortho. Why that way? Because para is more likely to be substituted. Okay, so halogens are para-ortho directors. Okay, if we look at activating versus deactivating, what do halogens do? Almost all para-ortho directors we would expect to be activators because they have electrons that they can donate into the ring. However, can halogens push electrons into the ring? No. If anything, they withdraw it from the ring. So halogens are in this weird gray area. They deactivate your reaction, but they're para-ortho directors. Okay, they're the one exception when it comes to EAS reactions. All other EAS reactions, if it's an activator, it's para-ortho. If it's a deactivator, it's meta-directing. Okay? Questions about EAS? Okay. Aspirin synthesis, as far as the mechanism goes, I do not expect you to be able to do a beginning to end like I do with the EAS. Okay, that's not going to happen. What you can expect for mechanism questions from the aspirin is the individual steps. So if you take a look at your group activity, verbatim, some section off of the group activity. Okay, drawing the arrows, providing charges, that kind of thing. Okay, from one species to the next. The other big question that you could get in the aspirin synthesis is the role of the acid catalyst. What does the catalyst do? What's the easy answer? What do most catalysts do to a reaction? They speed it up. So that's the easy answer, which would not be the one I'd want. Sorry. Our acid catalyst is an acid, so it's H+. Our catalyst works because our oxygen lone pairs can share, whoops, drew it off my screen. Okay. Works by doing this, which then puts a positive charge on that oxygen. Does oxygen want to be positive? Not yes, but no. Isn't there a game like that? Charades or something? Okay. We can draw a resonance structure where we can put positive charge on our carbon. A positively charged carbon is also known as, good answer, not the one I was looking for. Also not what I was looking for, keep going. Type of chemistry. It's not an acid or a base. So there's 6 definitions you should have memorized when it comes to organic chemistry. What a Bronsted acid is, Bronsted base, Lewis acid, Lewis base, and the phylls, electrophile, nucleophiles. If we put a positive charge on that carbon is now an electrophile. So the acid catalyst works by protonating our electrophile, making the electrophile more electrophilic. The more electrophilic something becomes, or the more nucleophilic something becomes, the faster the reaction goes. Okay? Because we're making our starting materials more charged or more reactive. Make sense? Okay. You might review over the rest of the questions from your in-lab. Yeah, from the in-lab in that case. The questions about dimerization of aspirin molecule or acetylsalicylic acid forming weird polymer things. Don't worry about those. Those are too hard to draw, so I wouldn't expect you guys to be able to do that one on the exam. Okay, so we're looking at relatively simple things. It's looking at ultimately the reactivity of the carbonyl, deciding electrophiles and nucleophiles. Okay. Questions about aspirin? Okay. We then get polymers. So as far as questions that I could ask here, pattern detection. So given the whole circles and squares things from that group activity, can you identify the reduced repeating unit? Okay, and try and identify the ideal circumstance. Okay, so if it was the sequence of all those circles, it's one circle. Okay, so make sure you can identify those. Based on grading that group activity, I saw a lot of people for this polymer drawing out the reduced unit as this, or sorry, not even that. Oh shoot. Something along these lines, or even along these lines. That's wrong for that polymer. What is the reduced unit for that polymer?
The circles at the end and then the squares at the end.
Our reduced unit ends up being this guy. What type of polymer is that? It's a copolymer. There's verb block copolymer. Okay, so you should be able to identify the types of polymers: simple copolymer, block copolymer. You should be able to identify the monomers within an individual polymer, both with circles and squares kind of a deal, and with actual molecules. And that one definitely gets a lot trickier. I'll pick the easier ones. Okay, so we'd be looking at your in-lab for the polymer lab. The very last page had 3 questions or 3 structures and asked you to draw polymers, I think. Those are going to be the key ones to go from because the group activity had some really tricky ones in it. So I won't ask you those really tricky ones. Okay. You should be able to identify the polymer mechanism, addition versus condensation. What's the red flag for it being an addition polymer? So given the monomer, what would you expect for an addition polymer? What do you need to see for a functional group? Alkenes. What would you see in the polymer? It's an all-carbon backbone. When it comes to the condensation, what do we see in the monomer? Carbonyls, or the carbonyl functional group. When it comes to the polymer, what would you see in the backbone? For lack of creativity, not all carbon backbone. Okay. So there were a couple possibilities there. Some people, I think I heard someone say it, seeing a nitrogen in the backbone. So you'd be looking at, very similar to your protein chemistry, forming the amide. You could also see oxygens in that backbone, in which case you've got a polyester. Okay. So as soon as you see not all carbons, you're looking at a condensation. All carbon backbone is addition. Okay. Questions about the polymer? Oh, experimental setups. For the addition, so back to the addition polymer in lab, what things were important about the experimental setup there? What you need to get that reaction to go? You needed light. Okay, so your addition polymers in most cases are going to require light, so that would be a big red flag if I asked you what experimental condition is going to stand up. You're looking for light. The other things that you could see from the addition polymerization reaction is what physical characteristics did you notice for that one? Well, it ended up being a very solid, chunky thing. Okay, so it stuck to the slide and very, very hard. Okay, why was it very, very hard? It's not just the carbon backbone. It was the cross-linking in that polymer. There was a cross-linking unit that allowed that polymer to form a very hard, rigid substrate. Okay. When it came to the nylon, you didn't have cross-linking, so you had a softer polymer. Okay. What else was really important when it came to the nylon lab? The 2 phases. Okay. You controlled how the polymer was formed by having the polymer only form at the interface between those 2 phases. So you made sure your reagents were in 2 separate phases. Okay, so that was pretty huge. Okay. Other than that, I think the polymer lab is pretty much beaten to death there. Other questions about it? Okay. Proteins, I expect you to have 3 amino acids memorized. with their classification. The most important thing to me when it comes to these amino acid memorizations is their classifications. I want you to know how that protein or that amino acid will interact with other things. So you're looking at its intermolecular forces. Okay, so that's its primary focus. Because you'd need to know the intermolecular forces, you might need to have the structure memorized. Okay, or you could have it memorized based on name, the 3-letter code, or even the 1-letter code. Okay, so as long as you have some combination of the classification, its intermolecular forces, and one of those other possibilities, structure, name, 3-letter, 1-letter, you're okay. Okay, which is, I know, is slightly different than what I said in lecture. Okay? Questions about the memorization requirement? Beyond that, there's not a whole lot to talk about. You're looking at what things cause the protein to change its shape. So you're changing the physical environment in which that protein was. So you added heat, you did acid-base chemistry. How did those things change the intermolecular forces causing the protein to fold or unfold? Okay, so it's pretty much answering the questions from your in-lab for that. Group activity, no, yeah, that'd all pretty much be in-lab questions for the protein lab. Okay. Last thing with classifications on that, if I drew out a protein structure and then boxed in, that was on your group activity, right? Where I had a protein structure and had boxes around certain areas and asked what intermolecular force. Does that sound? You guys at least saw that question, right? That type of question is fair game. Okay, which ultimately comes back to this. If you know the classifications for your amino acids, you should be able to tell me the intermolecular forces, which goes all the way back to the general question at the very beginning. Okay, if you know your intermolecular forces and the bond types and the structures, if I draw out some big complex structure and then ask you to tell me what intermolecular forces, you should be able to do that. Okay, and that's ultimately what this protein lab was looking at as well. Okay, questions about that? Yes? There's really nothing I can do about that now. Yeah. What I would say is I've got office hours, or you can send me questions via email. We can make sure that you've got your understanding correct with those.